Hi guys, good day, and once again welcome to another video lecture for our class, Fundamentals of Mechanics, Fundamental of Deformable Bodies. Alright, so basically what I wanted to do in this video is to introduce what the subject course, course is all about, as well as to discuss the first two topics, in which case the conversion of units and as well as the introduction to stresses. Alright, so first and foremost, what is this subject all about? Allow me to share my screen first. Okay, so fundamental of deformable bodies. Mechanics of deformable bodies is a study of the internal effects of stresses and strain in a solid body that is subjected to an external loading. This course deals with the actual stresses, strain, and stresses for torsion, thermal expansion, bending stresses, beam deflections, indeterminate beam structures. So basically, what is these stresses, or what's the focus of this subject is the relationship of the stress and strain and how does it affect a material or a certain material, not just any structures, or for example the beams itself. It may apply to all materials. Let's just go ahead and have a demonstration, for example, or visual demonstration. Okay, so for example, you have a piece of steel that you wanted to stress, or you wanted to pull each side. Alright, so when we are pulling each side, we are already applying external forces. Now, the deformable bodies, or the study of deformable bodies, focuses on what those forces, basically effects, or the effects of those forces that you have applied in the material that you are stretching. Okay, so basically, in order to do that, we need to understand the stress and the strain relationship of the material. For example, you are pulling again, you are pulling a piece of steel, and as you pull it breaks. It basically breaks into two. Okay, so after you basically applied a minimal force, it already the steel is already expanding. But then again, due to the elastic deformation, it just remain after you release the force, after you release the tension, the bodies remain, or the material remain to its standard dimension. But then again, when you exceeded, when the force applied already exceeded its elastic limit, and basically it already passes to a plastic deformation, or a permanent deformation. So that is why, after it is stretched too hard to its maximum capacity, it breaks, in which case it ruptures. But don't worry, because we are going to talk more, or we are going to discuss more about that in the next topics. But for this video, I'd like you to focus on our first two topics, in which case the conversion of units, and as well as the introduction to stresses. Alright, so here we go. Basically, for the general course goal, course guideline and regulations, and as well as the grading system, you already have, I know that you already have read this class orientation course. Okay, so I'll just go ahead and skip that one, and for this video I'll just go ahead and go to the conversion of units. And by the way, why I am skipping this one, because I wanted to keep this video as short as possible for you to save your data, or for your internet connections. Alright, so conversion of units. General principle. Okay, general principle in mechanics, we use four fundamental quantities called dimensions. And what are these four fundamental quantities? Basically, we have the mass, the length, the time, and the force. Alright, so we have US customary units and as well as SI unit, in which case In Philippine setting, we usually use SI unit, no? But occasionally we also use the US customary unit. All right. So for mass, no, for mass, we have this dimensional symbol M. For length, we have the dimensional symbol L, and for time, we have the dimensional symbol T, and force as F. All right. So in SI units, no, mass is measured in kilograms, in which case the symbol is kg, or small letters kg, and meters is small letter m. Second is measured. Time is measured in seconds, and the symbol for seconds is in s, no, small s. We have Newton, which it symbolizes as capital N. Now in US customary unit, we have the slug. The symbol for slug is slug also, no? And we have foot, FT. The second is still S, no? And instead of Newton, we measure the force, or customary force, as pound force, no? Pound, or LB. Alright, so in SI units, or the International System of Units, abbreviated SI from the French system, no? International Unites. Alright, so it is accepted in the US or United States and throughout the world, and is modern version of the metric system. By international agreement, SI units will replace our system or system. Alright, so prefixes lang. When a numerical quantity is either very large or very small, the units used to define its size may be modified by using prefixes. Right? For example, 4 million newtons, we can just represent that one as 4 meganewton. Alright, so mega newton. Or 0.005 meters as 5 millimeters. Alright, so basically, I just want you to be acquainted of these symbols, as well as the exponential form, the prefixes, and their symbols. Alright, so for multiple of billions, we have giga. Millions, we have mega. Thousands as kilo. And sub-multiple, we have 0.001 times 10 to the power of -3, in which case we call that one as milli. Micro. If we have basically 1, 2, 3, 4, 5, 6, 6 decimal places, and nano for 9 decimal places. Okay. Alright, so nano is a little bit smaller than micro. Alright, so kindly familiarize with their symbols. Giga as capital G, mega as capital M, K as capital K, kilo as capital K. Right? So milli, M, micro, mu, nano, S, N, small n. Alright, so with that, let's just go over with some few examples here. I already showed the solution here, so I'll just go ahead and read this one to you, read this out to you. For this video, I am just going to discuss thoroughly the first example. For the second example, I know that you can do this one on your own. The steps is already presented here, so you can basically just follow all throughout the example, right? So conversion, why is it important? Again, conversion, because conversion of units is very important, because we are not just using one type of unit, in which case we're not just using, it might be time, it might be combination, usually combination. Now for example, this one, convert 2 kilometers kilometer per hour to meters per second. Alright, so determine how many feet per second is this. Alright, so basically we are given 2 kilometers per hour. We want to convert that one into meters per second. And afterwards, we can convert that one to feet per second. Alright, so 2 kilometers per hour, we know that since km, k is 1,000, no? 1,000 meters, no? 1,000 meters. Therefore, we can just go ahead and multiply 2 by 1,000 meters. Okay, so 1,000 meters is equivalent to 1 kilometer, in which case we can cancel out km here and maintain the unit meters. Alright, so next is we want to convert hours into seconds. Alright, so we know that 1 hour is equivalent to 60 minutes and 1 minute is equivalent to 60 seconds. Or sometimes if we don't really want to have a very lengthy solution, then we can just go ahead and use 1 hour is equal to 3,600 seconds, no? So you can also use that conversion, no? 3,600 seconds. 1 hour is equivalent to 3,600 seconds. But for simplicity, no, or so that you can follow this conversion, no, I tend to write to convert hours to minutes first and then minutes to seconds. All right, so 2 hours, or sorry, 1 hour is equivalent to 60 minutes. Okay, sir, bakit or anong nasa ubos ang minutes? Remember that the unit hour is hour or nasa sa ubos. Therefore, in order to cancel that one out, no, we want to put our conversion on top, no, to cancel 1 hour. Right? So cancel 1 hour here. What remains is 60 minutes. And remember, the minute sign or the minutes is our denominator, so we want to cancel that one out also. So 1 minute is also equal to the 60 seconds in order to cancel the minute units. So cancel, and cancel km, cancel hours. What is left is meters per second. Now the answer is already there, 0.56 meters per second. Alright, so if you kindly just verify, kindly verify with your calculators. Alright, so this will be my my answer for the first part of the question. Now there is a second part. Alright, so we want to know how many feet per second is this, no? 20 km per hour is how many feet per second. Alright, so you may also convert km to feet and then convert hour later to seconds, or you may just utilize the meters per second, because basically it is much simpler, because we already know that 1 meter is roughly around 3.28 feet, no, per meter. Alright, so since we have 0.56 meters per second, all we need to do is we just need to convert meters to feet, because the second is already good for our units. Okay, so converting meters to feet, we just need to multiply 3.28 feet in our 0.56 meters per second. Okay, in which case we can get 1.84 if you want to if we round it up to 2 decimal places. And then for this one, I just chose to round it up to 4, no? So 1.8368. Now, sir, common question. Sir, how many decimal places should we answer, or should we put our final answer? So I would say, no, when you are still doing your solution, when you are still utilizing the decimal places of the solution, I would like you to utilize 4 decimal places. But if ever you are in the final answer already, if you are already in the final answer, I want the final answer to be 2 decimal places only. So this should be, since this is 6, round up, no, this should be 1.84 feet per second. So basically, that's it for our conversion examples. For the rest of the example problems, no? For the rest of the example problems, I would like you to go over this one on your own. I know that you can just go ahead and follow the directions, no, on the conversions itself. All right, so I'll just go ahead and open this assignment for you to do. No? I'll just go ahead and clear the dates. And then let's go over to the introduction to stresses. Alright, so introduction to stresses. What is this stresses all about? Okay. So mechanics of materials, no? Stress, chapter 1, stress, fundamental areas of engineering mechanics. Alright, so first and foremost, before we go into detail of what is really the deformable bodies all about, no? Let's compare this one to how is it different from statics and dynamics, sir? Okay, so basically statics and dynamics is the study of external forces upon a rigid body where the change in shape or deformation can be neglected. It uses the equation of equilibrium, no? So equilibrium equation, all summation of forces should be equal to 0 and summation of moments should be equal to 0. Alright, so mechanics of materials. It deals with the internal effects and deformation causes by applied loads. So what's the difference? So summing up the moments in a pin support, no? At a pin O determines the value of P. In this solution, we assume that the bar is both rigid, the deformation of the bar is neglected, and strong enough to support the load W. Right? So in mechanics of material, the statics solution is extended to include the analysis of the forces acting inside the bar, but the bar to be certain that the bar will neither break nor deform excessively. Alright, so this is the thing that I am basically referring to, no? So if the load is much greater, no, greater than the weight W, no, is much greater than the bar that it can hold. Basically, this bar will deform permanently, no, will deform permanently. All right, so like that. Okay, so basically, sir, unsa man gid ang difference statics and dynamics considers the external forces, no, without considering the internal effects of the materials that we are using, no. But in mechanics of materials or fundamentals of deformable bodies, we are already analyzing the deformation, no, the elongation, the difference, or the difference, it might be shrinking, no? It might be shrinking if we apply basically compressive forces. It may compress, and then it may shorten the material, and or if we tend to put tension or tensile force on a certain material, it will elongate. So basically, in the deformable bodies, we are also determining what is the elongation, what is basically the deformation that happens when we apply certain forces to a material. Okay, so deformation produced by internal forces. So we have basically, I'll just go ahead and summarize this part, no, by analyzing these images, no. So basically, in statics of rigid body, if we apply forces here, no, for example like this, no, we applied here, no, there will be no elongations, no, or we will not consider the elongation that will happen to a certain material. Okay, so undeformed, no, this is the original state of our material, or any bar, no, or round bar perhaps, no, or any material or circular material. Okay, so this is the undeformed section, no? And then if we apply a tensile force, in which case this is fixed, no? Fixed support na siya diya. If we apply tension here, basically it will elongate our material, no? Because we are pulling and the other side is fixed, no? So elongate, it will basically elongate. And then shearing force, no? If we apply perpendicular force to a material, okay? So there will be shearing force. Alright, so twisting. So it is also a common deformation. Where, sir, asa man na siya, sir? Asa man na ito makuha, no? You might, twisting or twisting internal force is also known as the torque, no? Twisting stress, twisting force, no? The twisting force is, we also refer that one as torque, no? Torsional, no? Torsional stress. Alright, so torque. So basically, if this is the undeformed material, then it is slightly rotating, no? Slightly rotating to the point where the twisting is going, no? It might be clockwise or counterclockwise. Alright, so slightly lang here, but if we elongate or if we expand the material to maybe about 100 meters, this may twist, no? This may twist more, no? Magkataas gani ang atong material class, mas dali na to siyang i-twist. Alright, so bending moment, no? Bending moment or the effects of bending in terms of the internal force, no, of our in the material. If we bend our material upwards, no, if we bend our material upwards, basically, no, it will cause this bending. All right, so this bending deformation is very important in the field of civil engineering, because we want to know or we want to determine if the capacity of the beams, no, the capacity of the beams to resist the bending load, no, the bending load will be able to carry out, no. Kaya if dili gani or if not, no, in the point of civil engineering lang, no. So if ever dili makaya sa beam, no, it will eventually crack. It will eventually crack. The beam will eventually crack, and the building will eventually fail, no, or collapse. All right, so normal stress. Let's analyze normal stress. Sir, normal stress, no? Normal stress is, we symbolize that one as sigma, no? Ito lang, no? As early as now, I would like to say that when we analyze stresses, it's always force, no? Force P over the area, no? Ano lang yun siya, no? Stress. Just keep that in mind, no? When we talk about stress, it's always force, and it's always over the area that is where it is applied. Now, what changes here, no? The shearing stress, the normal stress, or any other stresses that we are going to encounter next or to tackle next is the main question you need to know is, or you need to analyze is, what force is acting, no? And what area should I consider? Okay, so those are the things that you need to know, right? So for normal stress, it is the normal stress, and then actual force P, no? Actual force P, it might be in newtons or it might be in pounds. Again, during the conversion of units topic, we already discussed that these are the common customary units that we are using, no, newtons and pounds. And then the area of the cross section, no, area of the cross section. All right, so shearing stress. All right, so shearing stress, we usually represent that one as tau. All right, so V or the shearing force applied. Again, for the shearing force, it's always newton or pounds or in pounds, no? Or it might be the variation is kilonewton, no? Kilonewton, pound force, no? Pounds. All right, so shearing stress again, for the unit of shearing stress is basically just force over the area. So therefore, Newton per meter square, or in Pascal. The Newton per meter square is Pascal. Okay, so pounds per inch squared, or PSI. Okay, so pounds per inch squared. Okay, so area of the cross section gihapon, no, meter per meter squared, or square meter, or in square inches, right? Normal stress distribution in a strap caused by concentrated load. All right, for example, we have again, this part, I'll just go ahead and summarize this one into this section. So in what are the effects, no, what are the effects in this particular force P, no? If we have a fixed material here, no, fixed material, meaning to say it cannot move or cannot be taken out, no, or naka-fix kina siya diha, no, it might be a column, or basically welded na material here, no, and then basta dili siya maalsa, no, naka-fix siya na material diha. Alright, so fixed material, what is the effect, no? Imagine if you cut a cross section here, no? So for cutting of cross section class, no, I suppose that you already covered that one on your statics, no, statics of rigid bodies, no. You are already taught how to cut sections. All right, so basically what happens here is that this illustration cuts 3 sections, no, one in the upper section, second is the around here, middle section, and then here, lower section, lower section, farthest from the force P. All right, so here we go, no. So it is said, no, when we cut a section, closer to the applied force, no, the shearing max, or sorry, the normal stress, or the stress maximum, is around 2.58 pound force, no, per square area, no, per area. Okay, now when we are cutting somewhere farther, no, farther from the force applied, it is reducing, no, nagka-reduce siya, class, no. So the shearing max is around 1.15 force over area gihapon na siya, class. Now if we cut somewhere farther pagid, no, much farther pagid siya, it is basically 1.002 force, or P over A, no, force over the area. So imagine if you have a very, very large section, no, large section, and you cut it at somewhere, you pull it somewhere on the tip of that particular section, and then you cut it somewhere in the base, no, to just to analyze. So basically the shearing max will somewhat sum up to just force over the area. All right, so stresses acting on inclined section. All right, so there is nothing new here, no, walay bago direct class, don't you worry. The thing is, we just analyze this one into 2 forces na lang, no. We combined the normal stress, and the shearing stress, okay, in order to get this particular formulas, no, derived formulas. Okay, so if you're looking for inclined section, or stresses, or normal stress in an inclined section, then you may directly use this formula, no, P over A cosine theta over P cosine theta over A over cosine theta, in which case we can derive this one further, or simplify this one as P over A cosine squared theta. All right, so let us look at this one first, no, before I explain this shearing stress. All right, so the area, no, it's just the area that is changed here. Now, remember on the normal and shearing stress, we are looking at a cross-sectional area. Now, if we cut this one in an inclined plane, no, in an inclined plane, basically the area, no, the area, we just need to change the area itself, no, the area lang. All right, so the area and the force that is applied. All right, so for this one, no, since this is already inclined, no, our p cosine is here, no, we already distribute this one as our shearing, no, p sine theta, and our, since this is already inclined as I've established earlier, so this will be our p cosine theta, no, so this will be our normal surface, normal, no, perpendicular, p cosine, no, normal stress perpendicular to our area, and then p sine theta, in which case this is our shearing stress, no, shearing stress parallel to our area, no, our area of consideration. All right, so that's basically the difference, no. There's nothing new, no, nothing new. If we analyze this one, no, if we analyze this one in a very short one, no, in a basically in a shearing and inclined plane, I'll just go ahead and maybe change my screen, no, yeah, to demonstrate this one further to you. Okay, so I hope that you can already see my screen, no? So what I am talking about is like this, no? So for normal stress, for example, we have this area, we have this area of a this area, no, and then we applied a certain force. It might be usually tensile force, no, force P. Then our shear stress or normal stress should be equal to force over area. Now this area of consideration is here, no, this particular area, this area itself. Okay, so what happened, no, what happened if we cut an inclined plane? Okay, if we cut an inclined plane, therefore the area of consideration changes, no, changes. Alright, so ako lang ni bali, no, baliktad lang nato. The area here for normal stress is this one. Okay, so this area, for inclined plane. Ay, sorry. Right, so that is for our shearing normal stress, and then for our shearing stress, again, V over area. So for our shearing stress, it is the applied parallel force, no, parallel force V. So for this one, our shearing force, I'll just go ahead and make this one red for you to visualize clearly. So shearing force, in which case, again, on our slide earlier, no, P sine, sine of theta, and our normal force is P cosine of theta. Alright, so basically there is nothing new. It's just that the area, no, the area and the direction of the force were changed in an inclined surface. Alright, so anyway, you may use this formula, no, for your guide, or if you want to derive your formula, basically you will just go ahead and arrive with this much more simplified equation. Formulas, no? So for normal stress, we have P over A cosine squared theta, and for our shearing stress on an inclined section, no, we are going to have P over 2A, no? Twice the area, sine 2 theta. Alright, so with that, let's go ahead and make. So, shearing and bearing stress. Shearing and bearing stress. Okay. Shearing and bearing stress. Okay, so shear stress, again, we already talked about this one, no? T is equal to just the shearing stress over the area. Alright, so shear stress on the other hand is tangent to the plane on which it acts. No? Tangent to the plane on which it acts. Shear stress arises. Ay, sorry. Wala pa na ako makuha ng share screen, no? Okay, so this one. Alright, so shear stress on the other hand is tangent to the plane on which it acts. Shear stress arises wherever the applied load causes one section of the body to slide past its adjacent section. So that is why usually it is horizontal, no? If we analyze that one, if we analyze our section, the one that I draw earlier. Alright, so we have a lot of stresses or variation of shear stress. Now we have single, we have double, and we also have punching shear. Alright, so okay, explaining this one, we have single shear like this, no? We have two plates. We have two plates attached. Basically, this is the top view, side view, no? And then it is attached by a single bolt, no? Bolt. And then forces are applied on each plate, no? Opposite direction. So basically, this is a single shear. All right, so when it cuts the bolt, no, single shear lang siya. Okay, so force applied, and then the force that is resisted by the bolt is basically also force P, in which case that will be our shearing force. All right, now let's analyze double shear. Double shear, again, you have a yoke, no? You have a yoke here, a metal that is basically Y, no? And then you have a metal here, no? And we have a bolt and nuts and bolt, right? And you pull, again, we pull that one, or we apply forces. We apply force, no? We apply force on each direction, opposite direction, in which case the free body diagram of that, no, we want to basically simplify our shearing force, no? So for double shear, all we need to do is just to divide our force P into 2. Why? Because basically it is already supported by two sides, no? Naka two sides naman siya. So equivalent lang, no? P over 2 on this side and P over 2 on that side. Again, for this one, no, for double shear, always remember the principle of the principle of equilibrium. Okay, so forces going up should be equal to forces going down. So again, V over 2, since there are already two points having the shearing stress, no? So we also need to divide the force applied, or force P applied, into 2. Alright, so B is equal to P over 2 for double shear. And then for punching shear, okay, so we have this setup. And imagine yourself using a puncher, no? Punching a paper. So same concept, no? Basically, it is supported by a punch and a metal sheet, no? So when we punch that one, we get to have the area, no? The area of this punching material. So basically, instead of the applied force, it tends to be uniformly distributed force all throughout the area of the punch, no? So kana siya. Alright, so V again is equal to E, no? So all over, right? So to resist that punching shear. Okay. So bearing stress. What's the difference between shearing and bearing? Again, it is just their areas. So bearing stress, if bodies are pressed against each other, compressive force are developed on the area of contact. The pressure caused by these surface loads is called bearing stress. Example of bearing stress are the soil pressure beneath a pier and the contact pressure between a rivet and the side of its hull. Alright, so bearing stress, no? Bearing stress, like sigma B, no? Is just equal to our force bearing over the area of the bearing. Okay, so we can also say that if we analyze this single shear, no? If we analyze that single shear, it is just the force, no? Force applied over the area, no? Area of the bolt that has covered the bolt, no? So basically, in full illustration, no? In full illustration, this is our setup for single shear. Earlier, we pulled we applied tensile force on each plate, no? And then basically this bolt will shear, no, or will tear apart the plate. All right, so instead of tearing the bolt itself, the plate is teared, no? So there are two tendencies when you put a hole, no? When you put a, for example, just a paper, two papers, no? Two papers pinned by example, the bolt is a pencil perhaps, no? So since the bolt has a greater strength than the paper, then basically the paper will tear. So same, no? Same concept here. So let's apply that one here, no? So since the bolt has a greater strength than the plates, then the plates was teared, no? So we also need to determine the bearing capacity of these materials. Right, so again, the thickness, force P is just equal to the thickness times its diameter or bolt diameter. Okay, so because this is the part that is resisting the force, or the resisting the force P. Alright, so I suppose that's it for now for this video. Okay, so that's it for now for this video, class, and I'll be discussing more examples on another set of videos, because I think that this video is already too far, or medyo lengthy na siya. So I hope dili ra mo ma-board, no? So anyway, don't forget to learn, no? Have fun and enjoy. All right, so see you on the next video.